This is Bradford Donald Keller Townsend, and this is a Dyslexic Learners video, Exponent Laws. From Wolfram Math World. I'm a subscriber to Wolfram Alpha. I enjoy it very much, and for dyslexics I think it's a outstanding learner's tool. Maybe they'll give me a free subscription for just kidding. The web's most extensive mathematic resources, built with Mathematica technology. And you can see at the top here it says calculus analysis, special functions, exponentials, interactive entries, interactive demonstrations. So I just put in mathematics exponents, and it wasn't at the top. It was down like 10 in the list, but eventually there was one that said just exponent laws. Exponent laws, also called the laws of indices, Higgins 1998, or power rules, Derbyshire 2004, page 65, are rules governing the combination of exponent or powers. Now in previous videos we've used powers, but I thought it was good to go back and cover these laws. You have to know these laws inside and out if you're going to be doing a little bit more advanced math problems. So we have the base x times x, and each is to an exponent. So xm times xn equals x to the x plus m, and that's the language they usually use. So if this was a 2 and this was a 2, you'd have x times x to the fourth. If this was 3 and this was 3, you had a 3 for the m and a 3 for the n. This would add up to 6. Okay, now we have x to the m power, that in the numerator, and then a bar here, and then x to the n in the exponent. When you have a fraction like that, you subtract the denominator exponent from the numerator's exponent. The x in the numerator, so you get x to the m minus n. So if m up here was 5 and n was 3, you'd take 5 minus 3, and then that would be 2. Then we have x to the m with parentheses. This makes a big difference. Okay, it gives you a completely different answer. To the n, if there wasn't, if there were no parentheses there, then you would have probably the example up here at 1. So what happens is you multiply. So if it was x to the third, n was also a 3, you'd multiply those, and this would be x to the 9th. Okay? Now, here you have in parentheses x, y, and there's it's understood that that's time. Sometimes there'll be a little dot in there. You could also have a bigger x for multiply to the m. So that m carries to the x over here, and it carries to the exponent of the y. So it equals, so this is the same as this, x to the m, y to the m. Okay? And we're going to do examples, but we need to start off somewhere, and there's a lot here to unpack. Okay? Now we have x and y in fraction form to the n power. In this case, the exponent xn is on the numerator, and y to the n is in the denominator. X to the negative n is 1 over x to the n. Okay, so this negative goes away. You notice it's not in the right side. The left and the right side are equal. They mean the exact same thing. So x to the negative n equals 1 over x to the n. Okay, so this negative makes it into a fraction. It brings the x into a fractional form. Verdad? X over y to the negative n equals. Now this means it's the same thing. We still have the y went up here and the x went down there, so they switched the numerator and denominator, and then the negative went away. You see that? Flip-o, change-o, negative goes away. Again, x over y to the negative n, and the x and the y are in parentheses, equal parentheses y over x with the fraction to the n. So the negative sign went away, and we flip-flopped the x and the y. Where quantities in the denominator are taken to be non-zero, special cases include 1x to the 1 equals x, x to the 0 equals 1. These just have to be memorized. You'll use them in every other problem. You'll get an exponent of 0, and then that always equals 1, no matter what's in your x. It could be 1 quadrillion, or negative quadrillion, or 1 negative 3, or 2. If it's to 0, it equals 1. If it's any real number in here, it equals 1. And then x, anything to 1 equals itself. So negative 1 to the 1 equals negative 1. 0 to the 1 equals 0. 1 to the 1 equals 1. 2 to the 1 equals 2. 3 to the 1 equals 3. 4 to the 1 equals 4. And 5 to the 1 power equals 5. And negative 10 to the 1 power equals negative 10. Whew, okay. For x does not equal 0. That's what that equal sign with the line crossing through it means, not equal to. For x not equal to. So the definition of 0 to the 0 is 1. This is something that needs to be memorized, and you just have to know it. Just like you need to know that anything to the 0 is 1, you need to know that 0 to the 0 equals 1. And I said that when I used 0 there, but here they are again. That's good they showed that, because that would come up and bite you sooner or later if you didn't know it. Or you might guess it's 1, but you'll be like, oh, did I get that right on the quiz? Is sometimes used to simplify formulas. Now, a formula includes things that are not just equations. It's probably similar to an expression, but they're usually used in engineering and physics and chemistry for an expression that's not necessarily equal. But it should be kept in mind that this equality is a definition and not a fundamental mathematical truth. Okay? Now, in math, you can have 1,000 angels dancing on the head of a pin. It's not a natural science like physics, chemistry, and biology. You can have fanciful notions. We can do problems with elves and rainbow unicorns. And we can get answers that don't correspond with reality in mathematics that are mathematically correct. Math, it's hard to define, but it is a man-made creation. It doesn't necessarily correspond one-to-one with reality. So right on here at the beginning, we kind of have that deep philosophical maxim here. So 0 to the 0th power equals 1. Note that these rules apply in general only to real quantities and can give manifestly wrong results if they are blindingly applied to complex quantities. Por ejemplo, for example, parentheses here, that makes a big difference. I minus negative 1 to the power of 2, I, does not equal, these are called brackets, parentheses, I minus 1 squared to the I. So bringing what they're saying is that this 2 and I are paired, and you can't break them up like that. Now these are conventions, and people invented math, like somebody composes a piece of music or makes a sculpture or something. These are man-made conventions. Okay, you could make up another correct math that maybe follows different, but that'd be hard. First learn what's been developed over thousands of years. And they've done a pretty good job with all the geniuses that have devoted their lives to working out these systems. You'd be hard-pressed to come up with something better. But you kind of first need to get a good understanding of the well-established math, and these are the rules. In particular, for complex z, and maybe I'll do a video explaining what a complex number is, and z is commonly used, and it's like a cursive z instead of the other kind of z. It's a different font. And real a, and then there's a period there, I think. Or is that a comma? I was wrong, it's a comma. Okay. Hopefully the computer will increase the resolution. Sometimes it does and it doesn't when I blow up stuff, or expand it, make it bigger. In particular for complex z and real a. And then we have zia. That's to the z as a complex number to I and a. And then the a is a real number. Equals the e, and that's a special number, and it's very important in calculus. Now, I might do a video on that. Negative a, AGR, z, and AGR is usually argument. And an argument is like an input into a mathematical box that gives you an answer, a function. And then we have z, which is again a complex number squared, and it's to the power a divided by 2 in the exponent. And we looked up there what happens when you take something to a 1/2. That means you're going to take the square root of something's to the 1/2. You take like 9, square root of 9 is 3. Where ARGZ is the complex argument. Okay, I just wanted to get a video out there. It all kind of comes together. That's the thing, you might get a C in one class, and then you go up to the next higher course, and you end up learning a lot about the previous course because it uses, like there's a lot of algebra in calculus, and you get better at your algebra. So that's the end of this video. Thank you very much, and I'll be doing lots of examples. Thank you, and have a wonderful day.